Hi, I'm Charlie Thompson, and welcome to Chapter 11, Coastal Systems and Wind Processes. So here's what we're going to talk about in this chapter. We'll talk about global oceans and seas, coastal environments, coastal system actions, coastal system erosion and deposition, and wind erosion, wind transportation and deposition, living coastal environments, and then coastal hazards and human impacts. So the big questions for this chapter are, what are the characteristics of ocean and coastal environments? How do erosion and deposition by waves, currents, and tides alter the coastal landscape? How do erosion and deposition by wind alter the landscape? So this chapter is all about coastal systems and wind processes. How do living things, including humans, interact with coastal systems? So, part 1, global oceans and seas. So, oceans. Oceans are larger than seas. Seas are often partially enclosed by land. A gulf is a water body formed through tectonic forces and uneven erosion. They often have narrow openings. Bays and coves are similar to a gulf, but they're smaller. So I won't ask you questions like, is this a sea or an ocean? Oceans are bigger, seas are smaller, seas are enclosed by land. I'm not going to ask you about the difference between bays and coves and gulfs, although Gulf of Mexico, it's big. Emerald Bay, small. Here we've got most of the oceans and seas, like the Mediterranean Sea, the Black Sea, the Caspian Sea. We've got some gulfs, the Gulf of California, the Gulf of Alaska, the Gulf of Mexico, the Gulf of Guinea, Gulf of Carpinteria. And then we have oceans, the North Atlantic, the South Atlantic, North Pacific, South Pacific, the Indian Ocean, and then some smaller seas, North Sea, Greenland Sea, Beaufort Sea. But the biggies are the Atlantic Ocean, the Pacific Ocean, the Indian Ocean. And then we've got seas and gulfs. So the Indian Ocean, the Arabian Sea, the Persian Gulf, the Gulf of Aden, the Red Sea, the Mediterranean Sea, the Black Sea, the Caspian Sea. So seas enclosed by land. Gulf, often with a narrow opening. Chemistry of seawater. So you know previously that water is the universal solvent. Everything that water dissolves, all that water eventually ends up in the ocean. So anything water can dissolve is going to end up in the ocean. 99% of the chemicals in the ocean, chlorine, sodium, those are the biggies, chlorine and sodium. NaCl is table salt. Magnesium, sulfur, calcium, potassium, and bromine. Seawater is 3.5% salt, although that's usually listed as 35 thousandths, and we'll talk about that in a minute. So if you had a kilogram of water, 35 grams of that would be salt. 55% is chloride, 30% is sodium. The rest, sulfur, magnesium, calcium, potassium, and other trace elements. So seawater, on average, 3.5% salt. Salinity, sal is the root word of that, sal referring to salt. Salinity is the concentration, how salty something is. 35 parts per thousand, 3.5%. And some of the things that are going to change salinity, well, if it's raining, that's going to dilute it. If it's a desert, yes, oceans can be deserts. If it's a desert over the ocean, so there's lots of evaporation, the salinity would be higher. Places where there's lots of fresh water flowing into the ocean would be less salty. Brine is extra salty seawater. Brackish is water that is less salty than seawater. So when a river enters the ocean, you're going to have brackish water. And if you had an ocean in a desert region, you could potentially have brine. Brine would be seawater that's saltier than 35 parts per thousand. Nearest to land masses, water salinity drops due to freshwater influx. Again, that's just rivers running into the ocean dilute the salt. So this is cool. Here is a map of overall ocean salinity in grams per kilogram. So the green is 35 grams per kilogram, which would be 3.5%. So we have saltier, and we have also then less salty. There's regions that are less salty. So up it towards, well, under the polar front where it's rainy and cool, so there's not a lot of evaporation and there's a lot of precip. The water there would be, let's go back, brackish, less than 35 thousandths. And then over here you could have brine, brackish, less salty, saltier. So the saltiest part of the ocean is going to be here. Also some parts of the Mediterranean where there's lots of evaporation and not a lot of fresh water coming in. Salinity in high latitudes is dropping due to melting ice. We've talked about this before in the context of climate change. Let's go back to the picture. So Greenland is melting very, very rapidly. And so all of that ice is melting, becoming water that's running off into the ocean and making the North Atlantic less salty. Other changes to the ocean: acidification as the result of high amounts of carbon dioxide in the atmosphere. When seawater absorbs carbon dioxide, it becomes acidic. And so as the ocean is absorbing the carbon dioxide from fossil fuels, the ocean is becoming increasingly acidic. So here we have a map showing 2005 levels of acidity in the ocean. And here we have extended out to 2050 with a potential 500 parts per million. You can see the the blue areas adequate and optimal for coral reef growth, or any oceanic organisms that have calcium carbonate skeletons or exoskeletons. There's many microorganisms in the ocean that have skeletons on the outside. The skeletons on the outside are made of calcium carbonate. And as the water gets more acidic, those calcium carbonate structures can actually be dissolved, or the organisms can't actually grow those skeletons in the first place. So you can see that there's a big change here in the tropics with water getting less favorable because it's getting more acidic because the water is absorbing carbon dioxide. Ocean layers: as you go down into the ocean, it gets cooler, it gets saltier, there's changes in density, there's a mixing zone. Yeah, much of the ocean is empty, dark, and cold. Yeah, that's pretty much it. Most of the ocean is dark because it's below the limit that light reaches, and it's quiet. There's no currents because a lot of the currents in the ocean are surface currents driven by wind, so there's no currents, so it's just dark and it's cold. Thermocline, we'll talk about that. Deep cold zone. The water doesn't freeze even though it's below freezing temperature because of the pressure and the salinity. So two things are keeping the water from freezing: the pressure, salinity, because it's saltier. So most of the ocean, 80% of the ocean is in this deep cold zone. 2% is in the mixing zone where there's contact with the atmosphere. So there's going to be more oxygen. So here we've got a plot of temperature. As we go down, it's dropping from 20 Celsius, which is about 86 degrees, down to 0 Celsius, freezing. You can see carbon dioxide drops rapidly. So by the time you're about half a mile down, the oxygen has dropped dramatically and the carbon dioxide is increasing. So there's mixing in the mixing zone. There's some mixing between the mixing zone and the thermocline transition zone. But like I said, most of the ocean is just this deep, cold, dark zone. Yeah, things run off in rivers into the ocean like oil. Offshore oil drilling, single-hulled tankers, storm drain. When it rains, water runs off the streets, collects oil, goes into storm drains, and sometimes if it's raining hard enough, that just gets dumped directly into the ocean. So Here we've got a map of oil slicks and accidents due to oil tankers and drilling rigs like the Deepwater Horizon drilling rig that just dumped millions of gallons of oil into the bottom of the Gulf of Mexico. Renewables would stop all of this. Nobody worries about having a sunshine spill or a wind spill. We worry about nuclear reactors having accidents, and we worry about oil spills, but not the sun. Coastal environments. So let's talk about some of the components, the inputs. We've got energy from the sun. That's going to be wind. The wind is going to make waves. So solar energy creates wind. Climate regions are going to influence the temperature and rainfall. The characteristics of rock, going back to the chapter on weathering, rock that gets easily dissolved is going to get dissolved. Rock that is more resistant to chemical weathering will stick around and make good sand. Human activities. Are we making the cliffs steeper? Are we driving vehicles up and down the coast where there's oversteepened cliffs? Are we destroying mangroves? Are we destroying wetlands to grow shrimp, for example, in Thailand? Human activities, a big, big important. Are we building houses? All those human activities, very important. So same thing, human inputs. Are we building? How are we altering? Atmospheric inputs, wind and energy. We've got waves, we've got wind, we've got erosion, we've got transportation, we've got deposition. Just like everything that we talked about in the chapter on weathering and mass movement, we've got all that stuff. We've got transportation, we've got erosion, we've got transportation, we've got deposition. So we'll talk about erosional features like cliffs. We'll talk about depositional features like spits and bars. So some more definitions. The littoral zone, the coastal and shallow offshore area is called the littoral zone. The shoreline is actually the line of contact between the sea and the land. And the coast, the region that we're going to classify as the coast, continues inland from the high tide line, going inland to the first major landform like a mountain range. So we've got the littoral zone, that's the near shallow inland area. We've got the shoreline where the ocean actually meets the land, and then that's going to go up and down with the tides, high tide, low tide. Often there's a terrace. Often there's multiple terraces. In the wintertime, there's more energy from the storms, and so you'll have one terrace, and in the summertime, there's less energy, and so a different terrace will get built up. You can see this terrace is going to get flattened out by wave action. By the energy of waves, it's going to transport and deposit, and so you have this flattened terrace. We've got the surf zone, and then the coastal area goes from the high tide line. So here's the high tide line. That would be the beginning of the coastal zone, and then inland to the first major terrain feature, which isn't shown on this. What else do we need to know? Yeah, that's pretty good. The difference between the coast and the littoral zone, that's something you should know. Mean sea level. Value based on average tidal levels recorded hourly at a given site over 19 plus years. So there's this whole 19-year cycle, and once I show you what we're talking about with the relationship of the Earth and the Sun and the Moon, that's why we have tides. The relationship of the Earth and the Sun and the Moon. But for reasons I can't explain to you right now, there's a 19-year cycle of all the different possible combinations of the Sun and the Moon and the Earth. So it takes 19 years to work through all those combinations. So you can't really, you can't establish what an accurate sea level is in any location without measuring over that time period. Earth-Moon orbital cycle of 19 years. Tides vary daily. Sea level varies with a change in climate. As the ocean gets warmer, sea level's rising. As ice melts and runs into the ocean is also rising. So sea level is rising as a result of climate change. Let's talk about coastal system actions. Coastal system actions. Let's talk about the tides. Twice daily oscillations in sea level that vary in amount. So the moon's orbit around Earth takes 24 hours and 50 minutes. So every day the moon comes up 50 minutes later than it did yesterday. And tomorrow it's going to come up another 50 minutes later than it came up today. So if you see a full moon today, let's just say at 8 o'clock, tomorrow night the moon's going to rise at 8:50. Moon comes up about an hour later every day. It's really 50 minutes. The difference between high tide, between the actual level of the water with high tide and low tide, that's the tidal range. And different locations based on the geometry of the coast, how the shore slopes, is there a bay, all those affect what the tidal range is. So even along the coast of California, approximately the same latitude, you could have two different locations that would have really different tidal ranges. The Bay of Fundy, yeah, it's the winner. They have a 50-foot range. The difference between high tide and low tide, on a daily basis, the water goes up and down 50 feet. The tides are caused by the gravitational pull of the sun and the gravitational pull of the moon. So the sun's influence is less because the moon is way closer. The sun is way huger, but it's so far away that the gravitational attraction of the moon is more important. So the big bulge of water follows the moon. Tidal bulges are the areas of raised water. One is on the moon side. One is on the side facing away from the moon. So let's take a look at this picture. We've got either a new moon or a full moon. You can see the sun and the moon and the earth are all pulling along the same line. So we've got the bulge from the moon and the bulge from the sun. So you have high tides. And here, all the water is getting pulled away by the moon and the sun. So you have low tides. 6 hours later, higher high tides. 6 hours later, lower low tides. 6 hours later, higher high tides. And it depends on the time of the month, because it takes about 28 days for the moon to orbit Earth. So a week later, let me back that up. So if you had a new moon, when you have a new moon, what you're actually seeing is the dark side of the moon. We always see the same side. Earth and the moon. The moon is tidally, it's funny, tidally locked. So as the moon orbits the Earth, we always see the same side. So this side right here is this side right here. So as the moon orbits the Earth, we always see the same side. But as the moon orbits Earth, different parts of the moon get lit up by the sun. So in this case, this side of the moon is getting lit up by the sun. We see the dark side, so we say it's a new moon. A week later, the sun's going to be over here, and we'll see a half moon. First quarter, 1 week later, the moon will have a full moon, and we're seeing all of the lit up side. And then a week later, it's going to be down here. We have a third quarter moon, and then 1 week later, we're back to having a new moon. So when there's a new moon or a full moon, we have really high tides and really low tides. When you can see half the moon is pulling this way and the sun is pulling at a 90-degree angle. So the big bulge on both sides of Earth, high tide, low tide, but the little bulge from the sun is in the low tide. So the low tides are a little higher. Because this water has been pulled away from this bulge, the moon's bulge is the only high tide bulge, so the high tides are lower. I've thrown a couple videos. There's some, the videos are way better than I could possibly explain this, but if you got the idea, oh wait, I went crazy and stole these. So I thought this was cool. Put everything on one page and you can see if you're on Earth, this side, that side is facing Earth, that side is facing Earth, that side is facing Earth. It's always the same side. What changes is the part that's lit up by the sun and how we're seeing it. So there's a relationship between full moon and new moon and big tides, and then a half moon and lower high tides and higher low tides. So in this diagram, I put the pictures as it appears from Earth. So we're looking at a full moon, we're looking at a new moon, we're looking at a first quarter, third quarter. But really, that's the way it always looks. So the difference is which part of the moon, so that part's facing Earth, that part's facing Earth, and then I copied and pasted in actual moon photos. So when you're seeing the full moon, so now it's like you are looking at the moon from Earth. So the sun would be behind your head. In fact, in all these, the sun is, well, actually, no, because there's the sun. The sunny side of the moon is on the other side. We're seeing the dark side. That's a new moon. And then we see a quarter moon, and it looks like a D, and then an O, and then a C. So if you can remember Doc, the moon kind of looks like a D. There's the straight side. There's the curved side. Looks like a D, and then it gets bigger, and then you have a full moon like an O, and then it looks like a C, and eventually it'll go down to a sliver. So the pattern goes new moon, first quarter, D, O, C. Spring tide is when we have the highest high tides and the lowest low tides. Neap tide is when you have the low high tides and the high low tides. First quarter moon, third quarter moon, neap tide, full moon, new moon, spring tide. And then this is the Bay of Fundy. And let me speed this up. I mean, it's already sped up, and it's going to low tide. So what we're seeing, this animation would take about 6 hours. If we're going from high tide to low tide, that should take about 6 hours. And there we're done. And now the tide's coming back up, and now it's high tide. So that would have taken 12 hours. That should have been about a 12-hour period to go from low tide to high tide. That obviously was not a location with one of those 50-foot tidal ranges, but you can see that's a pretty big swing for the tidal range. Thank you, Bay of Fundy. More pictures, Bay of Fundy. There's another time lapse for you. Waves. Coastal system actions, waves. Waves are caused by the friction between wind and the ocean's surface. They range in scale from small to large storm-generated wave trains that radiate outward in all directions. In the open ocean, they're smooth, rounded waves. Those are swells. As the waves move, so here we've got swells, and when they run into something, there is refraction. The wave, the energy from the wave, in fact, I'll show this in a minute, but it's not the water that's moving, it's not the particles in the water that's moving, it's the energy being transferred from particle to particle. So really, waves are closest to the heat mechanism, the heat transfer mechanism of conduction. When the heat flows from molecule to molecule, the energy is just getting transmitted from molecule to molecule. So when these waves come in contact with the island, there's friction and it slows down. So this part of the wave slows down, this part keeps going fast, and so they end up getting bent in a mechanism called refraction. Here we've got two examples of refraction. This is Rincon. It's in Santa Barbara. You can see that the waves are coming in. I've got a better one. I like mine. So here you can see up at the top of the page, the waves are coming in parallel, but then as they wrap around the point, they get slowed down by the shallow water first, and so the direction changes, and now they're coming in at an angle relative to where they started, and that's called wave refraction. And I've put a video in there for you. So one of the weird things I mentioned, if you had a cork or a ball or a balloon or something and it was just floating in the ocean, it's actually just going to stay in the same spot. As the waves pass by, the energy is transmitted from molecule to molecule, but the molecules aren't actually moving. Other important things, that once you're below half the wavelength, there is no real wave action. So no matter how big the waves are, once you're, what would that be, half the wavelength? Once you're half the wavelength underwater, that wave action really isn't happening. This animation, and I've included this animation for you, the waves are coming in parallel to the coast, but then they're wrapping around the headland because of refraction. And that's going to work to concentrate energy here and straighten out the coastline. Again, Rincon, showing how the waves wrap around the edge. I've put this is in This video is in the playlist. I highly recommend it if you want more information about wave refraction, the way waves work to straighten out coastlines all over the world, concentrating energy, wave formation. Open water waves migrate in the direction of wave travel. The water itself doesn't move. The wave energy moves through the fluid. That's such a weird idea, because when you see waves, it looks like they're moving. And indeed, breakers move, but out in the open ocean, the water's just sitting there, transmitting energy from one place to another. As deep ocean waves approach the shoreline, the bottom of the wave slows down, the top keeps going until they trip and become a breaker. So as the wave comes in, there's friction against the bottom, and the top keeps going, and then eventually the wave collapses, making a breaker. Oh yeah, so I was hoping to find a video of a tank with a cork in it, but there's this just showing again that the molecules are kind of going in a little circle. They're just spinning a little circle. They're not actually moving along with the wave. It's the energy that's getting transmitted from molecule to molecule. Another type of wave is a tsunami, seismic sea wave. Tsunamis, sudden motions in the seafloor can produce seismic sea waves. Earthquakes, volcanoes, landslides, all of those can create tsunamis. Devastating coastal effects. Tsunamis in the open ocean travel very quickly, transmit enormous amounts of energy, and then when they come into shore, they do considerable damage. So here we've got an undersea earthquake triggering a tsunami, which in the open ocean you wouldn't notice, but they can travel 300, 500 miles an hour. So it would be a ripple 6 inches high traveling 500 miles an hour across the ocean. When they come inland, they slow down. This is the, actually I believe this was 2012, the magnitude 9 earthquake that triggered the tsunami in Japan. And I've included some of the videos. And when we think of tsunamis, we think, at least I think of big waves, but it really doesn't work like that. It's just the whole ocean is now higher and coming inland. So let's see if I can back it up until the good stuff starts happening. So earthquake, you can see it's just the whole ocean is moving in. There's not really anything going on. Oop, back, sorry about that. Try that again. So the ocean just keeps coming in. The ocean just, yeah, that wasn't good. So let's back that up. So here we've got the 2011 tsunami, or 2012. Well, they're calling it 2011. I'll call it 2011. 2011 tsunami in Japan. And you can see the ocean start to move. And this is really typical of a tsunami, that it's just like the whole ocean just moves into your house. It's not like there's a wave traveling at 500 miles an hour. It's just that now the whole ocean is here. So we speed it up a little bit. Water is still coming in. Now you can see a ripple. Water is still coming in. And here's a seawall that was designed to protect the city from tsunamis. And the ocean just keeps coming and coming and coming. Oh, right. And this is still playing it at double speed. Once, oh, you forgot to tie up your boat, dude. Water's still coming up. And that's it. It is now breached, overflowing over the wall. Let me slow it down to normal speed. And you can see it's just like the ocean is here now. That's all. The ocean is now just higher. And it just keeps coming and coming and coming. It's very interesting. In Japan, traditionally, they have had, and I was trying to back it up because there was a shot of the hillside. I wanted to talk about tsunami stones. That in Japan, because they are on a convergent plate boundary and they've had centuries, hundreds of years of recorded tsunamis. In fact, tsunami is a Japanese word. It means harbor wave, because that's where they noticed these. There was a tsunami in the 1700s triggered by the Cascadian Fault off of Oregon and Washington. Massive 9-something earthquake in Washington triggered a tsunami in Japan. And in Japan, like I said, they have tsunami stones. And so they've actually placed markers at the high water mark. And people were not allowed to build below the tsunami stones because that was the region, the area that would get hammered with these tsunamis. They stopped doing that because we live in a modern society now. But they probably should have kept doing it. Yeah, it's a 14-minute video. It's in the playlist. I highly recommend it, but you can see it just keeps coming and coming and coming. And I think I included... Yeah, let me go back. I don't know what I just did. Back. There was that. And then there's that. Coastal erosion and deposition. So I'll just leave that and say, I've put a couple of videos. I found a video actually taken by somebody in one of these cars that you can see floating away. And they're actually videotaping as their car was floating away in the tsunami. They were able to get out of the car and get rescued later, but that's in the playlist for you. Erosion is when weathered material is removed, and deposition is when it gets dropped off someplace. So let's take a look at coastal erosion and deposition. So you could look at coastlines in general and look at them as either erosional coastlines, emergent coastlines. So the west coast of the United States is an erosional coastline. Zones of active erosion. The east coast is typified by depositional coastlines. The west coast, there's that big boundary, the San Andreas Fault, the convergent plate boundary. We have an active tectonic margin on the west coast. On the east coast, and I'll show you this in the too long didn't read version in Google Earth, the east coast is continental crust, and it's attached to the oceanic crust of the North American plate. So the North American plate on the east coast is made up of oceanic crust offshore and then continental crust onshore, and it's all one plate. On the west coast, we've got an active tectonic boundary. So we've got a totally different coast on the west coast than we do on the east coast. Totally different beaches, totally different features, and we'll look at those in Google Earth. So erosional coastlines, you can have headlands like the Marin headlands, protruding landforms of resistant rocks, refraction, undercutting sea cliffs, headlands, sea caves, arches, stacks. Wave action will cut a horizontal sea terrace. So wherever sea level's at, the wave action makes it flat. So where the waves are flattening off, which would be the region between high tide and low tide. So every day as the tide goes up and down, that whole section is going to get flattened out. And for example, during the last glacial maximum about 20,000 years ago, sea levels globally were 360 feet lower. So if we drained the ocean and found the region that is 360 feet below the current sea level, that was the sea level roughly 20,000 years ago. So there's got to be a horizontal terrace about 360 feet below sea level. And in fact, in in the Google Earth tour that I'm putting together, you can see in Santa Cruz, Monterey County, Santa Cruz, these terraces, like if you enjoy Brussels sprouts and broccoli, a lot of that grown in Santa Cruz is grown on these wave-cut platforms, these wave-cut terraces. So this was sea level once upon a time, and it's been flattened off by wave action. So you've got a sea cliff. We've got arches. Those often don't last long, like the arch, the dramatic arch for the chapter opener has collapsed. So they're really temporary features. The headlands stick out, but then that energy gets concentrated, so they get worn away. We've got terraces. Right, erosional. Material's been removed, making a terrace. Material's been removed, making a cliff. Material's been removed, making a sea arch or a sea stack. So waves in deeper water move faster than incoming waves along the coast, which creates a current parallel to the coast that moves sediment in something called longshore drift or longshore current. So in this example, the waves are coming in and they're not coming in parallel. So when the waves come in, they're coming in at an angle, but then when the water runs back out with a wave, it runs downhill, straight back out. Gets moved in because, again, the waves are coming in at an angle, so it gets moved diagonally down the coast, straight out, diagonally, straight out. So it just sort of, the sand, the water, all of it just kind of zigzags its way down the coast. To where? You're probably wondering, where's the sand go? Well, either moves down the coast and makes a beach, or if there's a submarine canyon, the sand will go down that and disappear. So we've got a depositional coast with a bay. We've got beaches. The energy is concentrated at the headlands, so it'll straighten out the coast. The Nepali coast on the island of Kauai, one of the more beautiful coasts in the world. It's clearly lots of erosion going on here, and then deposition along the coast. Longshore drift can lead to a barrier spit. Tidal flats and salt marshes are coastal wetlands that get flooded and drained by tidal action. A lagoon is when you have a region that's cut off by, it's a cut-off bay, and it's cut off from the ocean by one of these spits. Ooh, a tombolo. A tombolo is a sea stack connected to the shore by sand. And I'll show you an example of a tombolo in just a minute. We've got beaches made up of sand particles brought down by rivers. Barrier beaches, a long, narrow... We don't really have those. Those are an East Coast thing. Barrier islands. It's a long island made of sand. They flood easily. We build on them. They get flooded in hurricanes, and we build on them. Also in the tour, I'll show you some examples of that. Texas, the Bolivar Peninsula, for example, when we were looking at hurricanes and storm surges, one of the examples was the Bolivar Peninsula in Texas, where the highest land is 6 feet above mean sea level. I think they had 15 feet of storm surge during Hurricane Ike in 2008. So a barrier beach, a long, narrow island that is parallel to the coast. So that would be a lagoon. This would be a bay barrier and a spit. It's not totally closing it up. This would be a bay barrier. So that could be a lagoon. That's a tombolo, which is a little island or a rock connected to the mainland by sand. Tombolo, tombolo. Beach, barrier, spit. A bay barrier is when it covers it completely. A barrier spit is there's still an opening. Oh, there you go, Russian River. Here's the town of Jenner, and we've got a barrier spit. We've got a tombolo, the Russian River. At low tide, let's see, how does that work? Yeah, at low tide, sometimes this is a lagoon. If the water level is low enough that this seals back up, you can get a lagoon here, and then at high tide, the ocean will actually go back up. So you'd have brackish water, right? Which would be water that would be less salty than straight up ocean water. So we've got a barrier spit, tombolo, coast, another typical coastal scene. Yeah, these are the barrier islands. These are just long, skinny islands made of sand, like there, flooding through Hurricane Irene, North Carolina. Yeah, just a bad idea. It's beautiful. The beach is wonderful. Great place to visit. I would not. Yeah. Would you buy that house? Would you buy that house? Would you buy that house? No, it's ridiculous. Sorry. 11.5, wind erosion. Let's talk about wind. So, Eolian. The word Eolian refers to wind. Deflation is when loose particles get removed and moved someplace else. Abrasion is the action of sand hitting rocks and abrading them away. So we've got an example of a wind-sculpted tree near South Point on the Big Island of Hawaii. Wind-eroded snow. Deflation. Desert pavement. It's a surface that exists in deserts when the sand gets blown. Right. So air is a fluid. And as the air moves, it transports material just like water does, just like what we were talking about in the last chapter about river processes. The same thing is true of wind. So water is a fluid, air can act as a fluid. And so, as you know from the last chapter, the faster the current, the larger material can be transported. So as wind speed increases, the wind is able to transport larger and larger material. But at low wind speed, the wind can transport silt. A little bit faster, it can transport sand. So if you have a surface made up of rocks and sand and silt, and you blow wind on it, eventually what's going to happen is the small material is going to get blown away, making a blowout depression, and the stuff that's going to be left are the larger materials that don't get transported. So here we've got sand and rock all mixed together, and two hypotheses. One of them is just wind blows away the small stuff, which leaves the big stuff. So eventually it becomes armored because the only material left is the stuff that's too big to get blown away. The other idea is that water does the same thing, that it washes the fine material away. And so all you're left with is pebbles and small rocks that aren't able to get transported. But this is a typical desert pavement surface. It's not sandy. The sand has been either washed away by water or blown away by wind. Probably both. As the sand is transported and it runs into rocks, it creates abrasion. And so some of the surfaces, the structures created by Eolian processes are yardangs. Those are wind sculpted features. They're large features, often enhanced by joints. And ventifacts. Venta is referring to wind. So ventifact, like an artifact, is something that's made by humans. A ventifact is something that's made by wind. So here we've got, that's not really a great yardang. That's a good ventifact, though. Here's a ventifact. This is, I think, in Algeria. Here's a ventifact. I believe this is in Death Valley. This is, I think, mushroom rock. So one of the things about wind and sand transport is that most of the sand, as it gets transported, it's going to bounce along the ground, and a mechanism called saltation. That's also how some of the larger of the smaller material gets transported in a stream, is saltation, the sand and stuff that bounces along the bottom. And it typically doesn't bounce higher than about a meter. So what's happening is about a meter, everything's getting abraded away. Higher than that, it's getting left intact. And so you end up with these fantastic shapes because up to about a meter, everything is getting blasted away, abraded away by the sand. Algeria, Death Valley, and I think this is also Algeria. And you can see just about 3 feet off the ground, everything is getting worn away much more aggressively than 5 feet off the ground. So ventifact, yardangs, wind sculpted, and you can see it's really big. I think that's the track of a car. So there are some tire tracks for scale. More yardangs. I believe this is China. More yardangs. So it's abrasion. Wind is just stripping away all the loose material. And wind is transporting loose material, like this is going to get transported. The large material is getting abraded. So the sand is getting thrown against the rock, breaking off pieces of the rock that then get transported, making more sand. Here's a yardang. And I included this picture because it looks a little bit like the Sphinx. Here's another yardang that looks a little bit like the Sphinx. Here's another yardang that that's the Sphinx. But there is speculation that the Sphinx was a yardang that was carved to look more like the Sphinx. So the face, the feet, they added that later. But yeah, totally obvious. Where'd they get the idea to carve that into a lion? Oh, well, kind of looks like a lion to start with, huh? Transport is material being picked up and taken for a ride. Saltation refers to the sand grains that bounce along the bottom of the ground. Surface creep, that would be like bed load, the equivalent of bed load, sliding and rolling. So we've got saltation, bouncing, surface creep, and rolling. It's exactly like, except we don't really have suspended load. I guess that could be silt, bed load, surface creep, but most of the material is bouncing less than a meter off the ground. In terms of deposition, right, so we're picking up all this sand, and we're moving it, and then it's getting deposited. Loess is a German word, and it refers to glacial silt. So all the places that were covered up by glaciers, underneath them have enormous amounts of ground up material. Fine sand, silt, larger rocks. And so the wind will transport that and deposit it. And there's large areas in China where people actually carve homes into these cliffs made of silt, the Loess plateaus. Sand dunes, where that sand accumulates, you get sand dunes, ripples. There are large areas of Earth that are sand seas. Those are called ergs. Although most of the deserts are actually rock. It's called reg. So here we've got the regions of the world that are made up of sand seas. The green, oh, right. Oh, God, look at that. Desert, steppe. The steppe has vegetation that is stabilizing the dunes. Here it's so dry the dunes just blow wherever they are. The Atacama Desert, Mojave, Sonoran Desert, Saharan Desert, the Kalahari, Namib, lots of Australia. Desert, desert, desert right there in the tropics. Desert, desert, desert right there in the tropics. And then the yellow areas are migrating dunes. So there's a dune. And deposition. Dunes move, the sand gets transported. Once the dune height gets to be about 30 feet, there's a steep downwind side called a slip face that will form. So there's a gently sloping windward side and a steep slip face on the leeward side. There's a bunch of different shapes for dunes depending on the direction of the wind and how much sand there is. So in this case, the wind is coming from the left, blowing toward the right. So that's a left wind. Here we have the windward slope with the gentle face. And then this is the angle of repose, right? The slip face is at the angle of repose. And so over time, the whole dune is going to migrate downwind as this sand gets blown up. And then the slip face, this gets picked up. And so we're just constantly creating a new slip face. And the dune is going to migrate in the direction of the slip face. So here's some different types of dune. Crescentic with horns that point downwind. Linear. Parabolic, like the opposite of crescentic. Star are the biggest, 3 or more radial arms. The monster of the desert is the star dune. You can have dome dunes. Crescentic, limited sand. So if you have wind coming from the same direction most of the time with limited sand, you'll end up with crescentic dunes. If you have tons of sand and shifting wind, you can end up with star dunes. If you have some vegetation, you can have parabolic dunes. If you have the wind that goes into 2 directions, like maybe that's going that way during the day, that way during the night, you can end up with linear dunes. Right. So last spring, I flew down to Arizona to take my son to a bike race and flew over the Sierra Nevada. So let's see. North is up here. South is over here. West is over here. The Pacific is out beyond the smog. And Nevada is over on this side. This is Mono Lake on the east side of the Sierra Nevadas. These are glacial moraines. We haven't gotten to glaciers, but a glacier came down that canyon. A glacier came down that canyon. A glacier came down that canyon and left these piles of debris. In fact, I was just talking about the idea that glaciers transport material. So this is all sediment that's been transported down by a glacier. This is all sediment that's been transported down by a glacier. This is a series of volcanoes. Bleep, 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 bleep. There's another view of this chain of volcanoes. And so you've got all this material being transported, being transported, being transported, being transported, being transported, being transported. You've got all this loose material, this sand, that then's going to get picked up and blown around. And I realized, oh, hey, that looks... So there's the Sierra. Death Valley's down here. These are the Eureka Dunes. And this is the view from Google Earth, looking at the Eureka Dunes. And again, the Eureka Dunes. So you can see the streams flow in. It's an area of interior drainage. So you have desert rivers that flow when it rains, picking up sediment, transporting it into these dry lake beds. And then after the storm, the water dries out and you've got sand that gets blown around. And some places it'll collect because of the wind direction and the topography and the valleys and the mountains. And so you get areas like Eureka Dunes where the sand is going to accumulate and you get these big, tall dune fields. Enough about dunes. Let's talk about living coastal environments. That's kind of an abrupt transition. So we've got corals. Corals are little marine animals. They have algae that lives in them that makes energy that they get. They make little calcium carbonate skeletons that form the coral reef, and then they die, and somebody else makes a home on top of them. So close up, these are individual corals. They're individual organisms that live together. And inside the coral, inside their flesh, there's actually algae that grows that makes energy from sunlight. So coral reefs, they produce large structures known as reefs, like the Great Barrier Reef off of Australia. Different reef stages. Darwin figured this out. This is fantastic. So I think I can explain all of this. If you add material to the top of oceanic crust, what you're going to do is then over time depress the surface of the crust because you've now just put stuff on top of the crust. So it's going to sink over time. So we've got a volcano in the middle of the Pacific being formed. And in the shallow water on the outside of the island, coral is going to start to grow. As the coral's growing at the same time, the island is sinking. And so the coral grows up at the same time the island is going down. So the island gets smaller and smaller until eventually you go from just an island with no reef to an atoll, which is reefs with no island. There's an island down there, but it's sunk below the waves, the combination of isostasy and also a wave erosion, right? Both of those over time are going to wear the island away, and then you're just left with the reef, and the reef is constantly being recreated by the living coral organisms. So coral reefs you'll find in the tropics. You need to have clean water. It needs to be warm water. That's why they're in the tropics. Corals from 30 north to 30 south, they need sunlight for the algae to grow, otherwise they die. Warm water, clear water. And if conditions get harsh, the coral actually kicks out the algae and then they die. It's called coral bleaching. And it's happening all over the world as a result of rising temperatures. All over the world, coral reefs are in trouble. The Great Barrier Reef is undergoing massive die-offs. I'll find a video and stick it in the playlist about the great die-offs on the Great Barrier Reef. which is horrible because coral reefs are incredibly productive. I mentioned before, 80% of the ocean is that deep, cold, dark ocean with not a whole lot going on because there's no light and there's not a lot of nutrients, so nothing's going on. The coral reefs are where there's light, where there's nutrients, where there's life. And so it's double tragic that coral reefs are being harmed by global warming because they are the nurseries for little baby fish. They're incredibly important for productivity in the ocean. Australia's Great Barrier Reef. This is the location of different reefs, different coral reefs, and you can see like from 30 north to 30 south. You can see it's below the ocean, so if sea level increased, which it is, the coral is just going to keep growing and growing and growing. If sea level dropped, then it would get exposed into the air and die. Farther, if you move from the equator to the poles, moving towards the poles from the coral reefs, you end up in coastal wetlands. So those are coastal areas that are wet, and they can be salty, they can be brackish. In estuarian environments where a river is emptying out into a lagoon or a bay by the ocean. Salt marshes are what you get, or mangrove swamps, salt marshes and mangrove swamps. So if it's too cool for mangrove swamps, you're just going to have a salt marsh. Mangrove swamps in the tropics. Salt marshes grow north of 30 degrees, common along the east coast, often in estuaries with brackish water. Mangrove swamps grow in the tropics, so they cannot survive freezing temperatures, just like saguaro cactus. So that would be a salt marsh. So we know that we're north of 30 degrees. So there's reeds, there's vegetation, incredibly productive because there's lots of water, there's lots of light, there's lots of life in these marshy environments. Here's mangrove swamp, and you can see how they would act as a nursery for baby fish, also like a coral reef, lots of places for little baby fish to hide. Mangrove swamps are also important in absorbing energy from hurricanes, and across Florida, across the East Coast, in the tropical regions where they actually used to have mangroves in Florida, they've largely been cleared for housing. So there's nothing to absorb the energy of the hurricanes when they come in other than people's homes. Coastal hazards, human impacts, well, sea level rise, we've talked about that. Potentially hundreds of millions of people dislocated by rising sea level. New Orleans, Florida, Miami, all those places. Bangladesh. Sea level rise is a coastal hazard. Storm surge from hurricanes, another coastal hazard. Erosion. In Alaska, climate change is causing more erosion because in the winter, the ocean used to freeze solid. And if the ocean's frozen solid, you don't get waves. But if the ocean is liquid and you have a big storm, then you can have big waves that can erode away these coastal bluffs. And there's at least one village in Alaska, a native village, that is having to relocate after existing for thousands, if not, well, at least hundreds of years. Hundreds of years people have been living in Shishmaref, and now they're having to move everybody to someplace else because of rising sea level, because of warmer oceans, because of increased erosion. Beach protection. Right, so we talked about longshore transport, the idea that the sand is going to get moved by currents down the coast and go someplace else. Well, people don't like that. In fact, globally, sand for beaches is an issue because where does the sand come from? Well, rivers, right? It's alluvium. It's material that's being transported by rivers, except when we build dams on the rivers, those dams act as local base levels. Those local base levels reduce the velocity of the water, and so you get the sand being deposited in reservoirs, which fills them up. So you've got reservoirs that are being filled with sand, and you have beaches that don't have sand. So they have to get the sand from someplace else, and they have to make structures to try to keep the sand where it is. One of those structures are groins and jetties. Breakwaters, right, because the ability of water to transport material depends on its velocity. So if you build a breakwater to calm the water down, it's not going to be able to transport sand as easily. Beach nourishment is the term for buying sand from someplace and then filling up the beaches. It's a short-term solution. It is not a long-term solution. It is very expensive. It is temporary. So here we've got some groins. In this case, you can see the waves are coming in, and the longshore transport would be from, in this case, from right to left. Here's Lake Michigan. They've got a series of groins. You can see the transport is going from right to left and then building up this big spit. So here's a groin with deposition, erosion. So there'd be erosion and deposition and erosion and deposition, erosion, deposition. And that's it. That's it for the chapter on oceans and wind processes. I hope you enjoy it. I hope you like the Google tour at the beginning, and I hope you like the chapter.